Thank you, Shiri. Thank you all for coming here. So despite everybody in the audience speaking Hebrew, I'm still going to do it in English. So sorry for that. So I'm going to talk about two recent projects that I was involved in. Both of them are in the areas of PCPs. So let's get slowly into that. So what are PCPs? So let's see some place where they appear in. So this is in the task of verifying computations that I hope that everybody here is somewhat familiar with. So suppose that we have a very complicated computation, and on the slide, this is depicted by a circuit, which looks very complicated. It's a logical circuit. God knows what's going on there. And, a computation has an input, X, and it has an output, Y. And, X is fed into the circuit, stuff happens, very complicated. Y output, Y is being output. How do we know that Y is the actual output? Or maybe it's just some garbage. So in other words, how do you verify that the computation on X is indeed giving you Y? So, this is a fundamental problem. It appears all over the place. And from the world that I come from, which is computational complexity, we sort of think about it as the idea of the class entry, where you want to show a witness that something which may be complicated to verify it by yourself is actually true. So how do you go about verifying something like that? Well, you need to provide a witness, or I'm going to use interchangeably the word proof. So you need to come up with a witness or a proof W that shows that indeed, if you feed X into the circuit, Y is the output. Okay, so let's look at this proof thing. So what is a proof? Proof is just a sequence of bits, or more generally, a sequence of symbols. The symbols in this talk are going to be from some finite alphabet, but not necessarily just 0s and 1s. This is in this example. And this witness should satisfy two properties. The first property is the completeness, which states that if the computation on X indeed gives Y, then when the verification goes to this witness and checks that, then it's going to say, yeah, this is the correct computation. The second property is the soundness, which says that if the computation was made incorrectly, then no matter what witness you give me, the verifier is still going to reject. So saying it more succinctly, completion soundness just says that correct computations are accepted and incorrect computations are rejected. Okay, so what sort of witness can we come up with? Okay, so before that, so these are the two very basic properties that you want. But once you have these properties, you may ask for more. So we want three additional properties. The first one is called locality, which I'm going to define soon. The second one is called efficiency. And the third one is going to be called succinctness or shortness. So what do all of these words mean? So let's start with short, which is the simplest. So we want the witness W not to be too long. We want it to be as short as possible. And we soon see what is as short as possible. So what is local? Well, local means that the verifier looks at only a handful of locations at W, does something, then looks at some other handful of locations, does something else, and so on and so forth, until it decides, okay, I accept or reject. In other words, each time it performs some local check. And finally, the word efficiency means that the verifier is efficient. It doesn't run for too long. And usually we think of polynomial time as something that is efficient, but in this talk, we're going to go beyond polynomial time. We're going to go actually to like constant time or something like that. Okay. So these are all of the properties that you want. So locality, as I said, you look at a handful of bits, do something, then some other bits, do other things, then another bits, do more until you accept or reject. So what would be a naive witness? Well, the most naive witness is just give me the entire log of computation of the circuit, and I'm just going to verify it by myself. I'm going to verify that first line implies the second one implies the third one, and so on and so forth. So this is the correct witness. It's completely sound, but other than that, it's nothing. It's not local, it's not efficient, and it's not short. It's just very naive. Okay, and again, you know, we haven't done anything interesting here. You may as well run the computation yourself at the same cost. So let's do something else. So now we come to, you know, major theory in computational complexity from the 70s, which is the Cook-Levin theorem, which in these words tells you that there is some other witness, which is more sophisticated, that, you know, achieves at least one of these properties. It achieves the locality property. So in other words, you can encode a witness to this verification problem in a way that at least the verifier is local. He only looks at 3 bits at a time. So can we do better? So now comes another major result in computational complexity, this time from the 90s. This is called the PCP Theorem, and it tells you that you can come up with an even more sophisticated encoding of the witness, which is also efficient. And by efficient, I mean the verifier is only going to look at 3 locations in the proof. That's it. So of course there is a catch here. The catch here is that now we're talking about randomized verification. So the verifier is going to be some random thing. He's going to check to choose 3 locations somehow, whatever is written there. And based on that, decide to accept or reject. And what's going to be the case is that if the computation is correct, the verifier accepts. And if it's incorrect, it's going to reject with some significant probability. So this is the setup. This is what PCP is about. Now I'm going to say the same things in a different language.
When you're mentioning locality, you only care about locations in the witness. Reading the entire input is okay?
The input is okay, but I'm caring about the witness.
And you never care about like what computational cost is computing the witness.
Depending on who you ask. For today, I don't care about it. For other talks, I mean. Okay, so now I'm going to say the same things, but in a different language, in the language of Twisat. So Twisat is the following computational problem. I give you a formula, a 3CNF formula, which is just an end of ORs where each OR consists of 3 variables or their negations. And the problem is to decide whether phi is satisfiable or not. Namely, is there a Boolean assignment to the variables that satisfies all of the clauses? So another way of stating the Cook-Levin theorem from last slide is that 3SAT captures the entire complexity class NP. In other words, for this talk, if you're able to do this witness encoding theorem for 3SAT, then you've done it for the entire class NP. So may as well focus on 3SAT. So how do you verify satisfiability? Well, this is, you know, when you prove that 3SAT is NP complete in computational complexity class, it is an NP part and it is NP hard. So this is the part where we show that it is NP. Well, a witness is just the assignment. The witness just tells me x1 gets value 1, x2 gets value 0, and so on and so forth. And then how do I verify it? I just go over the clauses one by one. Each time I read 3 locations from the proof, because there are 3 variables. I check that the clause is satisfied, then I go on.
So there seems to be a slight difference between these 2 formulations, because in the first one you see you have both the input and the output.
Mm-hmm.
But here you essentially have the output, but you don't have the input.
So
whether there is
so when you run the Cook-Levin reduction, it takes like the circuit and the input and formulates it as a formula phi. So somehow this phi encodes within it both the circuit and the input.
yeah, but still there's no difference between the other 2 formulations.
I think it's equivalent, but maybe
No, so what's the input here and what's the output?
No, so okay. Maybe I said it wrong. Okay. This is a decision problem.
Okay. So
The input is just 5, and the output is satisfiable or not.
yes, everything. So maybe it's not exactly
Okay.
an instance of the.
Okay, it's not an instance, but in spirit it's equivalent, and also in terms of complexity of doing this task. The complexity of the verification there is completely equivalent to the complexity of satisfiability. Okay. Thanks, Will. So yeah, so this is equivalent to what we said earlier. This is the encoding scheme, which is local, but besides locality, it doesn't have anything else. So it's not efficient because you have to literally read the entire witness. Okay, so now let's move to the randomized verifier model, and we're going to do it slowly. So I'm first going to do something which is very simple, which is just construct a randomized verifier, which is not very good. So I'm going to convert the previous verifier into a randomizer, and I'm going to do it in a very simple way. Instead of going over the clauses one by one, I'm just going to sample one clause, check the variables there. If it's satisfied, I accept. If it's not satisfied, I reject. So what's the performance of this? Well, if W satisfies 5, then I accept with probability 1. But if W doesn't satisfy 5, then we know that there exists at least one clause which is not satisfied. Probability I hit that is 1 over n, where n is the number of clauses. So all I can say is that I accept with probability at most 1 minus 1 over n, which is less than 1, but it's nothing to write home about. So it is local, and it is efficient in some strange manner, but the soundness is very weak. And you want to amplify that. So how do you improve now on the soundness? So now comes the PCP Theorem from the 90s. And it says the following remarkable assertion. It says that there exists another verifier, which I'm going to denote by VPCP, such that given phi, a formula, and some witness W, so the witness now is not going to be over 0, 1, but rather over like 0, 1, 2, 3, or something like that. I need a little more than 2. So it gets phi and a witness W. It only looks at 2 locations at the witness, and it has the following property. If phi is satisfiable, then there exists a witness that makes it accept with probability 1. And if phi is unsatisfiable, then no matter what witness you give me, the verifier is going to accept with probability bounded away from 1, most 0.9. Yeah, so this is now a big gap, 1 versus constant which is bounded away from 1. So this is really a remarkable theorem. And this is very useful for a whole bunch of applications. And there are a bunch of parameters here that I want to mention. So one parameter is the alphabet size, which is the alphabet size of the witness. Previously it was 0, 1. Now it's not going to be 0, 1. It's going to be a bit more, but still constant. I also want to mention that the length of W is somewhat blown out. Previously it was just n, the number of variables, but here it's going to be polynomial in n, which is good, but it's not great. And you have a gap between the completeness and soundness, which is nice. And as I said, we achieve locality and efficiency. And it's also sound, like the previous one. And it's a very powerful result. Right? You can start with this theorem and then prove a bunch of hardness approximation results. It's really useful. But once you have that, you can always hope for better. And indeed, when you look at applications, you start seeing what parameters play what role and what exactly do you want to improve. Okay, so let's now start splitting hairs and complain about the PCP theorem. So what sort of better PCPs you can hope for? So first, you can hope for better soundness. So 0.199 is smaller than 1, but you're not going to bet your life on a verifier that has this little bit of advantage. So you want something stronger, and indeed in applications, this is really crucial. And another one is you may want better length PCPs. So polynomial n is good, but n to the 100 is not that good. So usually you want something which is shorter. If I say the word practice, then you can need usually much smaller than that. So you can offer that.
So with little soundness, you can always amplify, so like
We'll get to that. I'm building it up. Yeah. So these two parameters come up in a bunch of applications. I'm not going to say anything about the application. I'm just going to put buzzwords on the slides. So it comes up in combinatorial optimization, in hardness approximation, in verification, as we already saw, complexity theory all over the place, and also in cryptography. So improving these two parameters directly translates into improvements in a whole bunch of applications in this field. Okay. So of course, one of the first ones to ask this question, and as Bill mentioned, you can do stuff. And now I'm going to tell you a little bit about previous works that we've done. So, right after the proof of the PCP theorem, people asked, oh, you have soundness 0.99, can you improve that? Can you amplify that by some way? And indeed, the parallel repetition technique, which is a result of Van Raz from 98, is exactly a result that does that. Well, I'm going to say exactly what it does, but basically it allows you to amplify the soundness into any number, any constant number. Like from 99%, you can get to 1% or 0.1%, but it is a catch. And after that, you can even achieve sub-constant soundness. By sub-constant, I mean that the soundness is a function that goes to 0 with n, something like 1 over log n or 1 over square root of n, something like that. So these are also some very nice papers, but there is a catch here. So if you notice, I discussed this, I highlighted this fact that you have 2 queries in your PCP. And this is something that you really, really want. And the caveat in this second line is that the PCPs here have more than 2 queries. They have like 3, 4, 5. And somehow you really care about 2 queries. So this is nice, but not completely satisfactory. And following that came, it took a bunch of time, sub-constant soundness PCPs with proper 2 queries. And this was first done by Moshkovitz and Raz in a very influential paper, and later was improved and redone by other authors. Okay, so now what about the length? So there is an early work of Polishik and Spielman that got a PCP which is almost of linear size, n to the 1 plus epsilon, but the soundness here was nothing great. It was close to 1. Following that, there is an incomparable result of Benson and Sudan, which gets an even better size, n times polylog, which I'm going to refer to as a quasi-linear size. But the soundness here is a bit worse. It's not even 1 minus epsilon, it's 1 minus 1 over log. So it tends to 1, but somewhat nicely, not trivially. And after that came a very, again, important work of Inu that showed the same size, quasi-linear size, but soundness bounded away from 1. Okay, so this sort of summarizes the works that were done previously. Oh, sorry.
By increasing the alphabet size?
We'll get to that. Sorry, I forgot to mention one more work. So the same work of Moshkovitz-Raz also gives you a PCP with small soundness and small size, but the size here is a bit larger than the previous one. It's n times 2 to the square root of log n as opposed to quasi-linear. So you can get smaller soundness, but again, you pay in size. Okay. So this is the existing work, and now I'm going to again explain more thoroughly about parallel repetition, which is most relevant to us. And indeed, you cannot amplify for free. You have to pay something. So let's talk about parallel repetition. Any question before that? The best would be linear size.
Linear size and left side.
Yeah, that would be the holy grail, and that would be an amazing result. But
It's dependence on left side of the right.
the constant, like O of epsilon,
Yeah.
the alphabet size and the size, like it's O of epsilon. And that's we'll get to that. Okay. So what is parallel repetition? So let's think about it. I have a PCP, it has soundness 0.99, and I want to amplify it. So what's the most obvious thing to do? Just split it. Okay. So the verifier is going to do, oh, I read two queries, I check them. If it rejects, reject. Otherwise, it takes two more queries, two more queries, two more queries, and I repeat it k times. And you can see that the soundness now will be at most 0.99 to the k, because each time you fail with probability 0.9. So you can take k to be large and everything is nice. And there are many things that are wrong here. So this is not one of them. Soundness is indeed at most 0.99. But the main issue here is that you've increased the number of queries that you made. Now the PCP makes 2k queries, and I already told you 2 queries is very important. So it is nice, but it's not satisfactory. So the fact that 2 queries is important, you can really only see it in applications. It's going to be hard for me to explain why that is. So you have to trust me on that. So how do you amplify soundness without increasing the number of queries? So this is the idea of parallel repetition. And somehow what you want to do is you want to exactly repeat this idea, but instead of doing it sequentially, like one after the other, you want to do it once, everything together. This is why the word parallel is. And it's easier, admittedly, it's easier to see once you formulate things in terms of interactions and provers and this and that. But I'm not going to take this language, so I'm going to attempt to explain it using witnesses. So for the verifier PCP, the witness is some string W1 to Wn. Now we want to construct a new witness where a single query to the witness would sort of simulate k queries to the previous one. So what you're going to do is, first of all, you're going to invent complicated notation, VPCP tends to k, which just means that you do it k times. And what's going to happen to the witness is that it's going to be much longer. And each location in here is going to correspond to k locations in the original one. In other words, when you read a symbol here, it's going to tell you what is the symbol in here, and here, and here, and here. So it's much more information. And therefore, because there are many more k tuples of locations, this witness is going to be longer. It's going to be of length m to the k, where m is the original witness.
No, why couldn't you do that to reduce 2 queries to 1 query in the original situation?
You have to check some sort of consistency. It's like okay, it's not clear why this should work, but you have to check some sort of self-consistency of the witness. And if you just look at one query, it's like, trust me. And if you look at 2 queries, like, you can check whether there is a collision or not. So, yeah.
Oh.
Yeah.
So why is link is implemented on m times k? That's k
So it's rather n choose k, if you want to be super precise, because it corresponds to choosing k locations from a universe of size m. So for each I1 to ik in m, you need a new location. So that would be it. Okay. So this is what parallel repetition is. And this is now a theorem of Van Raz, which shows that if you look at this new verifier, then the performance of it is very similar to the performance of the sequential. So if I satisfy the new verifier is going to accept it for 1, and if I is unsatisfied, then it's going to accept it for exponentially. in free variables, having a free variable is very powerful method, and I can spend a whole lot of looking for this.
You have to use something in the omega one. It's not 0.99, okay?
Yeah, so that's why I was
Right.
sort of sleeping, it's not like,
There's something that shows that it's not triple.
yeah.
And also the author.
So this is the data, but again, I'm going to compare about issues. So one issue is that the size of the proof increases polynomial. So if I want to drive this number to be very small, I'm going to put out k, which is about constant, and then I go from moving to size n to size n to the number is a lot. So in particular, we cannot get any size. And secondly, the alphabet also goes. So if the original witness was containing with a symbols from alphabet sigma, then the new one is telling me k symbols, so the alphabet is going to be sigma to the k, and the alphabet is sigma to the k. So exponential in k. This is fine, but what's bugging me here is that if you look at what's the alphabet versus what is the soundness, then you have this relation. But the alphabet is some q, the soundness is like 1 over q, some small number. So we want it also better that. So now this brings us to the two questions that finally considering these projects. Question 1, can you amplify with less lower side? The holy grail would be linear side would already ask terms. Anything else? Secondly, can you get better trade-off between the alphabet and the symbols? So for simple reason, we consider if you have an alphabet of size q, the best soundness you can put is 1 of them. So can you actually achieve it? Oh. So when you look at respect to question 1 is second doing. So this is then based on a recent joint work with Mitali Bafna and Nikhil Vyas, but it's based on some serious form, so it's based on some communication with Zigo Young, and previous forms by myself, Mitali, Noam Lifshitz, also independently in parallel with which people box it. So the result says that you can come up with a PCP construction, which is almost linear. It's quasi-linear, and at the same time it has small sums. Absolutely. In other words, it's good that you can build PCP, which is quasi-linear and simultaneously has small sums. And the proof here is it's complicated. So it's based on a bunch of things. I'm going to say some buzzwords, and then I'm going to explain about some of the buzzwords.
Is alphabet sense? Sorry, alphabet sense?
The alphabet size is exponentially 1 over x. So it's based on some ideas from regular expansion. The important testing, which we're actually going to discuss. And this is the thing that surprised me the most. It's based on some observations from this middle thing. Then you need some tools, large cameras, algebras, which is something that I don't know anything about. No, a little bit. So quaternions, chaotic numbers, zigzag products, you get some pseudo hardness and so take some mathematics. And now the second question, that website is Q, can you get one of the Q summers? But that's a little almost. So it's a joint over Kai Zhe Zheng. So we prove that for any Q, which is the power of 2, you can come up with a construction of the size Q. The size now is polynomial with the Q, and the frequency is almost 1, and sounds is almost 1. So I couldn't go. And again, it takes so mathematics in this case is full analysis, model import testing, some PCP stuff, and go for
In theorem 1, you have completed.
yeah, this. So before I tell you anything about the ideas, let me just tell you the application with this. In theory, just to get the context of well, some places that you care about. Okay, well, here we go. So using this, you can get better hardness approximation results if you are willing to assume the exponential time hypothesis. So exponential time hypothesis just says that P sub takes to the time. There is no better, there is no sort of exponential time. So if you're assuming ETH, you can actually get that even an easier format is still hard, almost exponential. So here's one example. For every epsilon greater than 0, if I give you a preset formula, and I promise to you that it's either satisfiable or either at most 7/8 plus epsilon satisfiable, two things that are very far apart, you still need almost exponential time. In other words, if you walk less than to the end of Fourier log time, you're still not going to be able to solve this even easier for you.
Or this was or
Before it was n over the square of something like that.
Doorway, 708 is 5 in one of clauses.
Yeah,
The
it's
sensitive
a
clause.
second clause. Okay, so this is, and you can come up with other assertion like that. This is just one example. So another application, which is not really an application of the theory, but rather of the techniques that go beyond it, is actually what we call distributed computing. So I'm going to say some words now, which don't mean anything, but they're going to mean some stuff later on. So there is an n-vertex graph with small degree or inorganic degree, which admits good routing protocol messages. So for now, we might be some vertices that want to send messages to each other. This is very good. There is a actually good way of doing it. So I'm going to explain more besides what it is later on. For now, it's good. Oh, no applications. No. There is application of the second result that tells you that what will kill your PCP this versus soundness trade-off. So first, this is an improvement of the previous results. So earlier, modern stuff was 1 versus 1 over Q with the 1 over 6 result. And later on, a very nice one, so a chart, the 1 versus almost 1 over 4 Q. Very often. And we get it all the way close to what is the optimal thing. It's sort of set as the optimal, get the better sounds. So secondly, this is motivation actually motivation for me to begin with. You get hardness result for quadratic programming. So quadratic programming is the following computational problem. And give you a quadratic form, it's just summation of every j, xi, j. Ignore that in that quiz. And the task is to find x that maximizes this form. So what's going on here? Well, I'm going quickly tell that we can get an log approximation. And this is a simple algorithm, but not trivial one. So like what the data inequality. So there's some STP stuff going on in the background. And as far as hardness results, this result of bottom sample that extended actually gives you a log n to the 1 over 6 quasi hardness. So the quasi just means that that is quasi polynomial and non-polynomial. That's it. And what you get from this theorem of power is actually the algorithm that gets log n approximation is always that. So you get quasi, and the average result of the factor log n, the 1 minus 8 of 1.
Why do you have to exclude the diagonal if the values are from plus minus 1 to the end, then the diagonal is just at a constant factor. The calculus is additive.
I think that you don't want to. So I'm actually not sure what is the precise answer. I don't think that you want to concentrate. That's
so Chan didn't give like another logo?
yeah. So that's the question. So Chan in some result, the dependency of the alphabet size is not that good. So now it's not sent to the cube, or when it was to the cube. So you couldn't take
The quasi will become exponential.
that. So for the suffering was good, but in China it was not good at all. Yeah. So finally, there are some connectivity problems where you use this result with networks, getting to the power systems. So I'm not even going to state it over here, I'm just going to give you a problem, I'm going to set it with some powers result. So example is the wanted connectivity problem. It's the following thing. The input is a weighted graph, okay? The root power, and a set of terminals here. Just what is the root and what you want to compute is the cheapest sort of divide, such that there is at least k lots which can pass from the root when it away. So if you want to compute the cheapest such divide in terms of base and power, then you can go for an approximation. Details of the subnomial approximations and also subnomial approximations.
So now you need to put it.
So for this quadratic form, if you know something about which A and J's are non-zeros and the algorithm that the relevant probability constant is sometimes later, say, okay, then you guess all of them are
No, we get some very special. So actually, this is what yes, gives you a generic deduction from PCPs. For many PCP constructs, we will well, okay, it's something very specific. It's not very reliable. Right. Cool. Any more questions? Cool. So we're so I'm going to tell you too much. So this is the slide of the results, and now I'm going to tell you about the questions. So what is that? First of all, it's a problem that was suggested by Sapphire 1000. And the reason that they came up with it is simplified the PCP. So the whole of this theory is quite involved and it makes sense to simplify it and maybe leave the problems. But if you don't care about that, it's the following very complete problem. Suppose that you have some function from 1 to n to c. So 1 to n, you should think about them as the variables of some formula. The sigma is the symbol 0, 1 or 0, 2, some small element. The direct point encoding little f is a map, capital F, that now takes k tuples of elements from n and gives k symbols. And it's just the most obvious thing. Capital F assigns to the set A1 to AK the values of little f at A1 to AK. This is the direct product way.
But this is a set, it's a subset, right?
Sorry.
On the left, it's subset, on the right, it's a vector.
Yeah.
Subset.
So let's think about if we have some ordering of n with this, and I want to AK of this according to that. It's not going to become clear by saying it as just for patient. Oh. So this is the encode. And whenever you have an encoding scheme, there is the testing question. Nobody promises you that they give you a G, which is actually recording to some meaning. Usually you have to test it. So this is the testing point. I give you some assignment from n to scale to sigma to the k, and I want you to test locally whether it is a direct product encoding of some stuff. And when I say it not locally, it means exactly the same as previous slides. You only want to look at a handful of locations. Not the column. And this math solution research in time series and they're useful. There were some references. But better than the references is the natural text that you can make. If you think about both functions, there is one very obvious right, which is the following. So if G is an actual valid encoding, some Nikhil, if I have some A1, it doesn't matter which setting it came from, it's supposed to get the same value. So what you're going to do is you're going to sample two sets, A and A1, that have non-trivial intersection. So it's followed. Then you're going to query G at what location and check that on the shared elements on A intersection A1, they are consistent. This is very natural test. Again, queries.
Why do you need more than a single element in the intersection for that?
Sounds very sounds. If you only have one, sounds we start.
Why think we should force growth?
Not one half, it's one over the size of telephone.
Okay, yeah, okay. I think I'll put out, but yeah, it's gone. So square of k is just some number between which is not too close to k, not too close to 1. Anything like that. There is an issue. Like if you take k minus 1 instead of square of k, then actually doesn't work. So you need something in between. It's a bit delicate. Okay. So this is the test, and here is a question more formally. Suppose that I have a G that passes the test with some non-negligible probability delta. What can you tell me about that? About G? Is it close to a direction point of some little f? Now I'm reviewing in corner to show that yes, in some sense. If G passes with probability delta, then there is some legal f such that G agrees with legal f on polydelta fraction of the sets A1 to A. So if you have delta agreement, then you have delta consistency with some orthogonal direct quantity. And this is the result, and you can actually use it for hardness simplification. But if I add individuals on, but again, still complain about it. So the main drawback here is that if you look at the truth table of capital compared to the truth table of beta, capital is much larger. It's roughly the size of F to the K. This is very similar to what happened in power repetition. When we did K power repetitions, the witness increased by exponential K. Exactly the same way. This is the combinatorial. Now we come to the question. How do sparse variants work? Can you use some different would be capital F, let's see. So Philip Kaufman suggested that high-dimensional expanders, you cannot really define it, you don't know what it is. It's very connected. That you can use these objects to actually come up with sparse objects that form like testers. But they couldn't only manage delta which is close to 1. And all delta equals 0 yes, for completeness. And they conjecture that there are some maybe other high-dimensional expanders, specific ones, for which you can take that will be arbitrary small point.
And the size would be not into the K, but
Yeah, but I said sparse, you know, yeah. And just to demystify it, what I mean is sparse, and what do I mean by HDX is just going to be some kind of level choice of the subset of the K sets that have both n sides, but somehow they are going to magically work. So really all of the cleverness goes into designing this polygon test. The test is going to be the same. The test is still going to be standard. It's still two sets. It's cleverly chosen set. they still look like intersect in group guide. Which check consistency. So what we can do here is choose this of test wisely. So both K of n is like K times n. What's to the K? To the K. I'm not going to go wide with chaos. It's not like a tower. And it's actually important. Okay. So this projection was recently developed by two independent time before. So one with Mitali Bafna and Noam Lifshitz, and another one by prediction approximation to and this is on a lot of course by much authors. And just to take it, the result says that whatever data you choose, you can actually come up with some clever choice of tests, where this test has some step. And this level choice of F is exactly S is exactly what all of the algebra, the adding numbers, quaternion, load. I'm not going to say anything about that, but this is the direct order. Okay.
This is just some high dimensional expander with over the property or something. So I mean, you can use it as a black hole.
So this is a high dimensional expander which wasn't what known before. It is an analog of the LSA complex, but over a different bit. So basically, start using something which is called type A buildings, and this uses type C. So, yeah, I don't. Yeah, we can talk about it compact. Some value. Okay. So now let me tell you a little bit about the dimension distributed coding. So again, I'm going to state some problems, which is not going to look relevant at all. Trust me, it is relevant. And the additional benefit is that you can look at this problem without extending anything for the answer. So far, it's really standalone problem. We have a graph. I'm going to call it a rounding graph because vertices and edges in the graph. And also I have a collection of C source pairs. These are S1 is T1 up to S2. And you should think of n as being linear and normal vertices. So what do I mean by source sequence? I mean that each one of the SIs wants to send some message to Ti. They want to report everything. And the point is that, not every vertex can send a message to anybody they want. They are only allowed to send messages on the edges of the graph. In other words, in the first round, S1 can only send a message to its neighbors. Second round, the neighbors can propagate this message onwards, and so on. So this is the game. You want to route these messages, and you want to construct the graph G, which works well. So what do we mean by this work well? So this is the most basic definition here. So we said that G admits in our round protocol, if there is some routing protocol for any choice of S1, T1, S2, that once it starts in our rounds, all of the messages get T1 up to T.
So the problem is like conflicts or something. No, just guesses.
On each edge, each time, you can only send one message.
Whatever you want. So we're going to get into more refined notion. Later, but for now, whatever you want.
So this is just the distance.
Yeah, for now, it's just the distance. I probably did make this weird things now, what I'm going to say is ridiculous. But let's say that you also don't want each vertex to receive to some business. Okay. Sorry, almost here. So later I'm going to call it. I'm going to have a note. So what you want is the first approximation is to design sparse graph. Because good routing of the code, we just need small r's. And as I said, you want more not only this. And once you phrase the question in a sensible way, that is really That's more interesting. So for that. But you can come up with a graph G. In fact, any graph G which is an expander would admit the routing protocol without the offload. This was for example by the Noam, shutting down, and mostly by Nado, so you will not spoil the thing, you will go. But the distinction is not too much important for us. So expander just does all the time. So okay, so this is the most basic question. And now we're going to slowly build it to the relevant model to us. So in our model, there are corruptions. Meaning, you run your protocol and some stuff goes on. You still want things to develop in the right way. So what do I mean by corruptions? So this is the most problem. So we still have the same setup. Still have a graph, you still have analysis of what the same messages is, and you can still only use the graph G. But now you have vertex corruption, which means that after the protocol is being set up, an adversary is allowed to control a small fraction of the vertices. And during the protocol, they can do whatever they want. They can not send messages, they can send garbage, points. Now your goal is to design sparse routing graphs, which are resilient against the corruptions.
It's deterministic, or you can.
The protocol.
Yes.
Yeah. So what do you mean by successful? I mean, for most of the pairs of SITI, the message is really going to be routed for. Some of them may be, next. Most of them are fine.
You do know which vertices are corrupted?
No. You set up the protocol, then somebody very malicious blocks whatever. So this actually problem was studied from the mid-80s in the crypto community or the community. And by now we know very good things. So we know the graph that has Fourier logarithmic degree and Fourier logarithmic for complexity, which is the notion I should have actually mentioned earlier. So raw complexity refers to how much work each vertex does during the entire line. So you don't want everybody to send the message to one vertex and be forward to the rest. That's all. Nonsense. So we want each one of them not to do too much work because people are going to get too many messages or send these messages. So this is captured by raw complexity. More formally, it's the computational complexity that the vertex performs.
So are you allowed to send the same message on various routes and then if at least one gets the okay?
Not at least one. The end vertex has to compute something out of all of this incoming inputs. So this is vertex corruption. Tell me that for us, the most relevant thing is edge corruptions, which is similar, but this is more general. So edge corruption is a more general model of corruption. Well, now, after you set up the routing protocol, the adversary is allowed to choose edges and corrupt them. And you can see this is more general because if I take a vertex and corrupt all of the edges, then I essentially corrupt the leaf. But this is more general. Now the adversary can propose a small fraction of that. So here there is only like one word, which is relevant. I'm not going to even state the results here. I'll just say that the parameters are good for us. Even if the parameters were good enough for us, still would be relevant, but still. So what we show here is that there are Fourier logarithmic degree graphs that have Fourier logarithmic for complexity and are resilient against edge functions, even from a pattern.
So are you assuming a lot of assumptions on corruptions? For example, what prevents you from corrupting all edges from a given vertex? And then how does it send the message?
No, so I don't need to succeed on all of the pairs. I don't need to succeed on all the pairs. I need to succeed on most of them.
Almost.
Yeah. Yeah, so you can take S1 and say, all of it without the edges of problem. So these graphs actually, they don't compare, as far as we know, they don't compare in the water. Actually come from these HDX graphs that we discussed earlier.
Like random bars. Random does not expected more.
I don't think so. So I'm going to say keywords why. So random fast. Yes, yeah. So some of this theorem is concerned, we currently got two bullets here. We already get two requirements from our graph. So we need a graph where we have good direct products in the graph. You also need to do the routing point for the sense that I define here. And the situation is a bit laughing in the sense that we really only want to know one graph that works. For one, it so happens to be the case if the circles work. So this is very lucky. Again, this starts with algebra. And this idea comes to fill in the table, like the chapter Sobotsky, and the graph that we consider are variance of this. So your question over this is the first. That's what they took there. Okay. So let me summarize the two main problems. So I told you about near-optimal soundness alphabet tradeoff, and also about quasi-linear discrete with small soundness, and I also told you about some application of them. And I explained some of the connection to the product testing and distributed configuration. As far as open problems, the only way to deal with linear size specifically with small soundness. It seems hard, never say never. And more, down to earth. It's fair to say that this is the first application of HDX in PCPs. And my belief is that once there exists at least one, there should be more. So are there any other applications of high-dimensional expanded in PCPs? And in particular of our routing technique? I don't know, I think that there should be. And so this is your question here. So the one word that I can say here about why high-dimensional expanders are good, as opposed to one of sparse graphs, is that high-dimensional expanders, with sparse, have large clicks, or large near clicks. And furthermore, these near clicks somehow expand between themselves also. This would not occur in a sparse graph. Just to give you a sense, these clicks, this routing coding, can be used for some sort of error correction. Like the message gets a click, they quickly communicate between themselves, there's an error correction, and they pass it on. So this is part of what's going on in our paper. It seems like a very basic idea, which should be useful in other places. I think we should again.
In power of an expander, I mean, cycling was an expander and the connecting any to each other of these sets of modes. But that is not.
So that's what we know that in 2007 later. But we didn't even know. Okay, that's